So this chapter, we've got our completed models, and then the goal of this chapter was just to figure out how do we push this to production, and they kind of laid out various different paths forward. And so this is something I haven't actually interacted with very much. I've done projects where I build a simple API and then I deploy something, but it hasn't always been super complex. I've done simpler things where I just need a single request to be answered over time. And so I can add a little bit of flavor text to some of this, but not a whole lot. So in the first section, they were talking about building something with Flask. Flask is a good, a lot of people use it to build websites and stuff, but if you want to, you can take just the API section of the code and it can help you build out a simple skeleton structure. You can just do your simple pip install Flask and that will get you most of the way there. And then they had sort of a template that you can follow along with, and that'll be pretty standard across any Flask app. And so you just take their starter code and then you plug in, here's how I load my model, here's how I do inference, and then it will do most of the handling in terms of requests and stuff like that. You just have to say basically, here's the URL that I want you to address, and then that will sort things out. One of the major downfalls that they listed is it doesn't allow for asynchronous requests. So you can have, if you're on the web, you can get multiple things backed up, and then you might end up in a scenario where your inference code is blocking your request code or vice versa. You can have problems with both directions of that. So it starts you off in a decent spot, but if you have more complicated requirements, then Flask might not be able to get you all the way there. I'm sure that there's some people have done all kinds of stuff with Flask, so I'm sure there's some way to do it, but it might not be as out of the box as the alternative that they laid out. So the second one they laid out, I've never heard this said out loud. I would say Sanic. This one is built to be lightweight. It's not necessarily, so Flask is kind of built to feed websites and do various other things. And I think Sanic is just designed to purely be the API section. And so in that one, it helps us do asynchronous and batch requests. And they kind of explain in more detail later in the chapter exactly what that means and what benefit that gives us. So with both of those options, they're trying to minimize the amount of time that they have to copy and transfer data. And then they're also trying to minimize the latency. So you don't want someone making a request to your API and then it takes 3 minutes or something like that. When I was doing a project a long time ago at my old Site 1001 company, we were doing this API that would take in a 1200 by 9000 image, and then it had to do convolutions over it, and we had to split it into shards, and and it was this massive process, and a single page could take over a minute. So there's a lot of things that you have to keep track of there. And then if you made a lot of requests, then you would end up with way too much data on your system, and you would end up crashing it. So there's a lot of different things that you have to be cognizant of here. It might not be as simple as some other web APIs where you're just saying like query this database and get a response on this tiny little bits of data. These can be fairly sizable, so you have to build with that in mind. One of the things they noted is the kind of standard base64 encoding isn't really great for sending images or a lot of the different kinds of data that we might send in a machine learning deployment. And so they were showing that you can use a put request and that will kind of send the more raw data. You don't have to base64 encode it. But with everything, it just depends on exactly what your format is. If you have some tabular data or something like that, it might make sense to still do that. next thing they were saying is that typically it's faster to process the requests in batches and not one by one. And that's useful for multiple different things. So it's useful in that you might not be blocking other operations if you just basically wait until you've got 8 saved up and then you do it all at the same time. But then at the same time, if you're doing inference on a GPU, we know that those are massively parallel, and then you can just say do 8 all at the same time, and it's going to take almost the same amount of time it would take to be a single inference sample. And so there's multiple benefits there, but you're also potentially making a trade-off in timing. So one of the things they listed later in the chapter is if you have some system and it's set up so that you do inference every time you've accumulated 8 samples, then you actually run the prediction that might be slower for the first sample because you have to wait for the other ones to arrive. And so you have to set some cutoff limit on that. So you have to say, if it's been over 5 seconds, that I'm going to just do the inference on the single sample, even though I haven't received a full batch yet, because you just don't have the requests required to fill that batch. And so the way they decided to organize this is you can split it into 2 different pieces. So you have one piece, one process that's running the requests, and then one process that's running the actual inference. And so the request process is just basically taking in the information it gets from the request and then passing it to a queue. And then what the inference piece is doing is it's looking at that queue, and then every time it's beyond your batch size or beyond the time limit, then it's doing inference, and then it's putting back the information of what your model returned, basically. And so all of that works with the async stuff from Python. I've worked on that stuff a tiny bit, but it's still a little bit foreign to me. I look at the code and I question it if it's even Python sometimes, because it uses a lot of decorators and it uses await and various other pieces of Python that I don't use very often. So if you were looking at the code and you were going, wait, I don't know what await, async, all of that stuff is, it's kind of a very specific branch, but there's pretty good documentation on the Python page for it. So if you just look directly at the Python documentation, it will show you what's going on, basically. And even after all of that, you get everything organized the best you can with the Python stuff. You still have some issues in terms of overhead and inefficiencies. So the thing that they mentioned multiple times, the GIL, the global interpreter lock. I don't know the full depth of that issue, but I know that there's issues with multiprocessing where you can't necessarily fully parallelize things. And so in the next section, when they talk about exporting models, they say basically you've gone as far as you can with Python. You need to get around that in some way. And so you can export it in various different ways to be used by C++ or different formats. And so the first thing they showed is that you can JIT, just-in-time, compile your model, and that will build in a whole bunch of optimizations for you. And we'll talk about the optimizations a little bit more in a second. So they showed that libtorch is the C++ library for PyTorch deployment. And then there's Torch Mobile, which is built on top of that, and it's just optimized for all of the mobile things that you might run into. Then they mentioned Onyx, and that's a pretty standard export format, and a lot of different frameworks are using this now. So TensorFlow supports it, PyTorch supports it, Microsoft's CNTK, a lot of different things support it now, and it's become kind of the standard way to export your models to this Onyx, and then you can deploy it in a lot of different ways. Then you just need something that can read and compute the Onyx graph, and then you don't have to bring along all of PyTorch or all of TensorFlow or whatever else you're doing. And even if you have a mixed environment, potentially you could deploy a PyTorch model and a TensorFlow model right next to each other, and all you need is Onyx. You don't necessarily need to have both of them present. And another thing I've seen is that a lot of people have talked about you export to Onyx, and then as long as you get the correct compiler or deployment system, it can get you a lot of speed up on CPUs or whatever target device you have, because it will actually use whatever code is relevant to that device. And so if you go from GPU to CPU, you might be able to still get decent performance out of it because it's written in a way that it specifically knows that you're operating on a CPU, and it will use a different version of the kernel or something. And so it looked fairly simple in the code. I can't necessarily speak to how difficult it actually is, but they said that you can just do torch.onyx.export, and it should generally work as long as you don't have some unknown operation. So we've seen in some of our PyTorch code, you can do all kinds of different crazy stuff with for loops and if statements and stuff like that. And so you have to make sure that whatever you have in there is something that's acknowledged by Onyx. Otherwise, you might run into problems. And then the other method they were talking about, you can do a trace using the torch.jit.trace. And that does a slightly different operation, but we'll talk about that in a second. And one thing that you have to remember with that is you have to turn off the gradient tracking. So you have to do with.torch or with torch.nograd. Otherwise, it will try to track the gradient even when you're doing inference, and you don't want to do that because it'll slow things down, and then it will also cause excessive memory usage. And so in that process of doing a trace, what you do is you give it some dummy input, and then it traces along the whole path that it took, and then it knows, here are the different operations that I need to do, and here's what the memory allocation looks like and stuff like that. And so the step after that, they were showing that if you do that trace step and then you put it in Torch script, that will help you get around the global interpreter lock. I don't know exactly why that's the case. I don't know why loading it in a different format helps you there, but that's what they're claiming. I'd have to learn a little bit more about that. Any questions up to that point? Comments?
Yeah, by the way, I didn't understand that either. I think maybe it's a C++ backend that's running the Torch script, not a Python backend that's running the Torch script. I think that might be why.
Yeah. I think that, it didn't really make sense to me because they plugged it right into the same Sanic code. And it seemed to me like that would run into all of the same sort of collision and multi-processing errors, because you would have multiple different things trying to pull from the same queue. Because that was my interpretation of where the problem would actually be, but I'd have to see more detail about that. I didn't look at the code in too much detail. And then so in 15.3, they're talking about interacting with the PyTorch just in time. And so they're showing that the just in time can have a massive performance change. And I've seen this personally on a couple different things. One of the guys I talk to sometimes, he maintains one of the PyTorch libraries that has all of the pre-trained networks for ImageNet. And he pretty regularly shows benchmarks where he's like, well, here's without the JIT, here's with the JIT, and all of a sudden it's 3 times faster and stuff like that. And so one of the things that they talked about in the chapter is that you can, the big benefit is you can combine certain operations. So if you take something that used to require the values being written down and then read back again, and if you can do that for multiple operations in a row, then you're saving a whole bunch of memory and IO. And so you can improve the speed a whole lot and potentially reduce the memory footprint. And so I've seen really big speed ups on that. And then they're showing that once you do the JIT version, you can call that with C++ or Python. And so you can do the base version or the JIT version. And then they had a discussion about scripting versus tracing. So my understanding of tracing is you kind of just follow along the path and then you say, I do this operation and then this operation and then this operation. And what they were showing is that that can do a good job, but it might be blind to certain scenarios if you have something that has like variable length or something like that. So they had a for loop and they said, this is going to iterate through this 5 times every single time. Whereas if you do scripting, then it will actually be variable and it can say, okay, this time I need to do it 12 times and this time I need to only do it 5 times. If you do tracing, it's just doing the same set of operations every single time. I haven't looked at the details, but that seemed to be my understanding of the scenario that they laid out. One of the other things they pointed out was with TorchScript, the language is typed. So it looked like everything could be inferred, but in certain cases you might have to explicitly say, this is a float, this is an integer, this is a string, this is a whatever. And that might help you in some way, but you have to know that beforehand, that it's expecting certain types and stuff. And then they started getting into the C++ section. A lot of this was kind of over my head, but my understanding of it is you can basically use some existing image library and that will pick up using their C image library, and then it loads in the image and you load in your model using this torch JIT load, and then you have your model and then you kind of run inference as normal just using C++. And then they showed snippets of the code, but not necessarily all of the code. And if you're interested in that, you can probably figure that out, assuming that you have some C++ knowledge, but ultimately probably isn't that important. I think for most people, at least, the important part on the data scientist side is probably understanding how do I export this in a format that is useful to either the web dev team or some other engineers that can then take your model and plug it into their C++ code in a certain way. And you have to be able to also communicate all of the assumptions. So one of the things they listed was the images can be loaded in all kinds of different formats. It can be 0 to 255, it can be 0 to 1, it can be channels first, it can be channels last, it can be red, green, blue, or it can be blue, green, red. And so if you are passing it off to a different team, it does have to be converted to C++. Potentially, you need to be able to well describe all of the expectations of your model. And then they talked about going mobile. So assuming that you got your model to C++, then there are various different ways that you can get it onto an Android device. It seemed like it wasn't too much work. Similar to the previous section, I don't really have the background in Android app development to fully say exactly what the complexity is here. But it looks like you basically just have to do some additional imports, and then you can do inference with the model blob that you've imported over to it. And then after that, they discussed 2 different techniques for making it more appropriate for mobile. So in our scenario, we had that massive segmentation model. You probably want to do something slightly smaller than that. One of the big requirements typically is the file size. So if you have a model that's 160 megabytes, putting it on a phone probably isn't that favorable and is probably going to be slow. And so what some people use is distillation, and distillation is basically take your old model and then build a smaller model to try to replicate the results of the old model. And so you can basically pass in the same training examples as before, and then you're just training on the predictions of the big model rather than directly on the labels. And people have found that you can get very good results out of smaller models starting with bigger models. There's one of the things they mentioned is DistillBERT. So we've got this BERT model that has been trained on all of this data and is massive and has millions of parameters. And then you can take DistillBERT, which is just trained to basically replicate it, but has like a tenth of the number of weights. And so that's kind of the idea behind distillation, is typically you can actually get almost identical results just with a smaller model by mimicking the old one. And then the other section that they were discussing is quantization, which is basically we might normally operate on float 32s, and you might be able to get away with downgrading that to a lower precision of a certain amount. And people have written some code that does a good job of making sure that you don't lose a whole ton of accuracy. But you, by reducing precision, you can get stuff as small as a quarter of the amount of compute typically. And it makes it way faster, and it reduces the footprint of the model, and it makes inference even faster. So that's a very useful skill if you want to push to mobile or some other embedded device that might not have the raw compute capacity that you need. And then in the last section, they were talking about there's various different vendors that are popping up that will help you with this serving of your models. So you've got your PyTorch blob, you've got your Onyx export, you've got your JIT trace. Various different companies are popping up that will help you actually deploy that to an API and make it easy. So you just upload the model, and then maybe you give them some data prep code, and then they'll handle the actual machinery of managing a queue and keeping the system alive and stuff like that. So that's it for the final chapter of the book. Any questions?
Has anybody used Streamlit before or heard of it?
I've heard of it. I've never used it. I've heard positive things about it. That's the one where you kind of have like the graphical tool that you can kind of drag and drop the pieces around.
Yeah, yeah, kind of. So it's I just heard about it like on Thursday, and I just put the link in the chat. But it's all Python, and you basically create like a user interface on your model, and I do this networking event called Lunch Club, and was teamed up with another guy who's a student, and they just like learned this. Kind of a interesting little. He deployed his on Heroku for free, and had like a data app. His was on sports, but it looks like they do object detection. They've got like one that's in their gallery. They've got like a face scan explorer, so you can like pull a bunch of sliders and like turn it into like a face using the GAN. Looks like a cool little way to deploy.
Yeah, this looks interesting. I'll have to check that out.
So Ryan, I was gonna comment/ask in that mobile section, they talk about quantization. So we've talked about quantization when you're actually training the model. It seems to me quantization when you're just evaluating and you're not having to worry about calculating gradients, that should be a lot safer, right?
Mhm. Yeah.
Like hopefully you don't have to worry about small values as much.
Yeah. Yeah. So some people have even written specific training routines now that are, they call them quantization aware. And basically it trains it knowing that it's going to be quantized at some point. And I don't know exactly what they do with it, but they do something so to minimize the performance degradation. Because you know that if something is very consistently right on the cusp of the difference between two different values, then the quantization is actually going to hurt it more. And so they do something in order to try to prevent that. But some people have even made differences in their training procedure in order to make it safer on the inference side once they do quantize it. But from what I've seen, people have a bad time trying to train a quantized model. Anyone want to give a 0 to 10 rating on the book now that we're completed? I'd give
I'll
it
jump. Go ahead.
I'd give it like an 8 or a 9. I thought it was generally good at teaching the concepts. I think that the first half was better than the second half. But I think it's good they showed the practical application of here's all the tools, now here's how you build a project. I just think that some of the stuff was a little bit I don't know how else they would have structured it, but they kind of just said like, here's the answer in a lot of scenarios. And I think it would have been better if they showed like, here's a simple approach. Okay, it doesn't work. Here's how we have to overcome this problem.
Yeah, Ryan, I think your assessment is pretty fair. I thought the first half of the book was great, and it did feel like it trailed off a little bit.
Yeah, for me, the second half of the book wasn't what I expected. So it wasn't necessarily in any way bad, but it was sort of like in the first half of the book, they're explaining like this is how, you know, PyTorch tracks gradients inside a tensor or whatever. It's like, okay, great. You know, this explanation is really helpful. And then in the second half of the book, they're explaining just as much, but they're explaining other things that aren't necessarily really PyTorch in my mind,
Mm-hmm.
you know? So like, I think I don't think it was in the meetup. I think you and I were just, you know, chatting or whatever. And I was like, I didn't expect so much like discussion of like, you know, F1 score as a metric, you know, versus like whatever
Yeah.
precision and recall. It's like, I don't think we needed that many pages. You could have just said like F1 score is good. And by the way, here's a Wikipedia page on F1 or whatever, or here's a good blog post.
Yeah.
You know, so it's like maybe if they had really stuck to the PyTorch explanations.
Yeah.
I do think on some level it's like nice to always have working code, you know? So if I want to deploy or want to whatever, here's like sample code, but I just don't know. For some of the things, maybe you don't necessarily need to walk through it as much. Just sort of say like, and here's the interesting things you need to know. If you want to see an example, here's a file.
Yeah. I think the other thing that I think I would have liked to see more of is the actual numbers and metrics of a lot of different things. Like they were showing in one of the last sections, they were like, okay, here's the metrics of things, and here's a list of things that have failed. How much better did it get when you did the various different things? And then like even on this one, they're talking about the amount of copying and the amount of latency and then the quantization and the distillation. It would be nice if they gave some numbers to it and said, we can reduce this model by 10 times and we only reduce 1% accuracy, or we gained this certain improvement in latency by switching to Sanic from Flask. And now we can do this. And I think that sometimes they listed off the things, but they didn't necessarily contrast them properly and give actual numbers to their comparisons.
Yeah, that makes sense. So I've yet to do my first from scratch PyTorch model. So I guess maybe the proof will be when I go to do that, then if I'm comfortable, then the book did its job.
Mm-hmm. Have you trained any PyTorch models at this point, like starting from someone else's work, or?
Yeah, but in that case, it was sort of like I changed very little about them, so I don't really take any credit.
Yeah.
You know, it's like I changed the data augmentations, but didn't really touch anything in the training loop. So it could have been like written in Sanskrit, and it would have been the same for me. You know.
Yeah.
I think when I first learned how to switch over to PyTorch, I followed this YouTube playlist by a channel, I think it's Centdex, and he has a whole like 10-part or 8-part series on pythonprogramming.net. He goes through it very simply of like, first you'll just create like a fully connected like neural net with just 4 layers, no activation, no nothing, just pass something through it. Then you'll be like, okay, now we need an activation function. Here's how we code that. And it was a pretty solid series from what I remember. It was just like very basic intro to PyTorch. And then I think eventually you'll do a CNN, but the steps they lay out and the code they provide is really solid to go through. If you do get stuck, I'd recommend it.
I guess one other comment for me is, as somebody who's actually built models before, this book was pretty well targeted for me. And so then like, here's how you do things in PyTorch. I think for somebody who was really new to machine learning, one of the things that that for me was downplayed is, imagine you're taking that Andrew Ng intro to machine learning class, right? And he makes you manually calculate all the darn gradients
Yeah,
and the
he
loss
does.
function, right? And then you're like, oh, and now here you can do this thing and you just say Autograd turn on, you know? And you're like, loss backward. Like, if you juxtapose those 2 lessons in an intro to ML class, people would be like, oh my God, you know, like what modern TensorFlow and PyTorch do with Autograd is just amazing.
They showed that a tiny bit, but they started with very simple equations. So we looked at the
It was the temperature thing, right? The
yeah,
thermometer or
I
whatever.
was trying to remember the name of the researcher that they used, but Galileo or something. But they had a very simple equation, and they said, here, we can just take the derivative of this. I think it would have been good if they said, here, take the derivative of this fancy equation. PyTorch can do it easily.
I linked that tutorial in the Zoom chat, by the way. It's pretty solid.